We've talked about some different operations in this unit, and we're going to talk about the last one today, and we're going to talk about more stuff involving the cross product tomorrow. So we're going to look at some of the properties and one of the versions of the cross product. Just like dot product, there's two versions of it. So we're going to look at one of them today and one of them tomorrow, just kind of shortening it. It also kind of gives us a bit of a buffer so we have a bit more time to prep for the test, I suppose. Because otherwise, today is a shorter kind of lesson, and so is tomorrow. One of the things we've talked a lot about is when you perform an operation, what is the result? So from a few days ago, there was question 5 and question 6, and I had some people coming in and asking about those questions and working on them and thinking about them. And as an example on the test, there's a very good chance the question would be something like, for each of the following expressions, what would the result be? Would it be a scalar? Would it be a vector? Or is it not possible? And perhaps if it's not possible, explain why not. Okay, just like those questions 5 and 6 from the homework a few days ago. So to get started, for these three operations that are all the three versions of different kinds of products involving vectors, and the first one is scalar multiplication, when we do a scalar times a vector. What is the result? A vector. And this is something you don't want to have to think about. You want to just know it. You want to really, really know it. What about the dot product? It results in a scalar. If you know the formula, we're going to confuse things a little bit more tomorrow when we do more cross product stuff, but if you know the formula for the dot product well, I mean that's not a vector. That's three numbers multiplied by each other. It's not a vector, right? So you could just deduce that the dot product is a scalar from that, but it's something you should know. And it turns out the cross product results in a vector. So there's all different versions and slight tweaks in how an expression is written will change whether or not it's possible. But if I did something like this, the cross product is defined with the X multiplication symbol. What do you think about this? I mean, we haven't even talked about the cross product yet, but remember? It's a vector. So what does this result in? A scalar. Can I take the cross product of a scalar and a vector? No, I mean, we haven't looked at it yet, but you can see the equation down here. You can't. The cross product is between two vectors, so this would not be possible. Okay, so that's an example of one thing that this is meaningless. This is not defined. Cross product is for two vectors only. And there's a few things, like always, we're going to talk about the different properties of the... Did you have a question or a comment?
So how do we differentiate the cross product with scalar multiplication?
You wouldn't use an X for scalar multiplication. You would just have like K times U. Like you would just use brackets or something. That's a context thing. There are probably people who would say they would interpret this as meaning, well, that's now a scalar, so I multiply it by that and do scalar multiplication. And so that might depend on, where you live in the world and the context, or there might be people who would interpret it that way. But it's maybe ambiguous, that kind of thing. But generally speaking, for our test, if you see this, it means cross product. It doesn't mean interpret it as needed. You know what I mean? Yeah, good question. Okay, so one of the things that the cross product does is a really important thing to know. It creates a new vector, like we say, the cross product results in a vector that is orthogonal to both of the input vectors. Orthogonal means perpendicular. It has a magnitude that's related to the area defined by the vectors. We're going to talk about that tomorrow, so we'll come back to that. Don't worry about that. So here we go. I'm going to talk about some stuff to do with orthogonality and things being perpendicular to each other. Okay? In 2 space, here are my 2 vectors. They're nice and pointy. They even have arrows on the ends, right? Here are my 2 vectors. So if they're in 2 space, they're lying flat on the table. Okay? And so I don't know that this is actually terminology, but I think you'll understand it, so I'm kind of making this up. But there's like a family of vectors that are perpendicular. If I just start with this as my vector, and I say find a vector that's perpendicular, there's an infinite number of vectors, but they're all collinear with each other. And they all would look like this. So there'd be some scalar multiple of this vector, right? So I could scale it up, I could scale it down, I could make it the opposite direction, but they would all be collinear with each other. So that's what I'm calling like a family of vectors. Does that make sense? Okay. And in 2 space, that's it. So there, like you could say there's sort of one vector and all its scalar multiples. Does that make sense? In 3 space, though, we talked about this yesterday, there's infinite, because in 3 space, I pop off the table, and I can rotate this vector around. It's a little bit hard to see on the camera, but I can rotate this vector around. These vectors are not collinear with each other. They're not necessarily orthogonal to each other. These 2 are, but not these ones that I'm changing. But this vector is always orthogonal to this one as I rotate it around, and all the scalar multiples of that. But if I have 2 vectors in 3 space, so I'm not going to hold them off the table, but imagine they're floating in space. There's, again, only one vector, family of vectors, that's orthogonal to both. What would it look like? I'm actually asking you this. New vector. Daniel. Exactly. It would be coming off the table straight up. So I'll try to show this a bit better on the camera. If these are like this, orthogonal will have to be like that. And I'll hold it up so you can see it just, right? That's how it would have to be. So, and then scaling it up, scaling it down, scaling it backwards. But again, that would be like a family of vectors that are all collinear with each other. That makes sense? These 2 don't have to be orthogonal. They could be. You would still have this one popping up away from the other 2, like that, to be orthogonal to both. So if you're talking about a single vector and looking for something that's orthogonal, you got lots of options. We looked at how you could do that yesterday, that little trick, by turning one of the components to 0. Orthogonal to both vectors, now we're talking cross product. Any questions about that? Here is one of the 2 formula. This is Cartesian space. The thing about the cross product is it is a little bit more complicated than all the other formulas and things that we've seen. Okay, so remembering it is a little bit easier. I'm going to show you a trick on which is an easy way to do the work, but it's also an easy way to remember the formula. So I'm going to show you that trick in a moment. But this one does require a little bit more practice. Dot product's pretty easy to memorize the formula. All the other stuff, magnitude, is all pretty easy. This one's a little bit harder. It's a little bit longer and less intuitive maybe. One thing that's interesting about it is if I compare it to the dot product. So again, the dot product results in a scalar, not a vector. You can see that this is a vector because it's got like an x part, a y part, and a z part separated by commas, and it's in vector brackets. So if I did the dot product, it would be a1, b1. Whoops, I meant to do it like this. A1, b1 plus a2, b2 plus a3, b3. That's the dot product. So if I compare these two, for some of you at least, this might help a little bit. Take a look at how the dot product is comparing things that are the same. So x's with x's, y's with y's, z's with z's, and adding them. So it's putting together the parts that are similar. And that's what the dot product kind of does. It compares the parts that are similar. What does the cross product do? It actually compares parts that are different and the difference between them. So look at for the x component. I'm using everything except the x's. X is a1, b1. That's not in the x part. Everything else is. So it's the y value of a times the z value of b. It's even comparing those parts that are different. Y to z, and it's subtracting, whereas dot product always adds. It's subtracting then the y of b times the z of a. So it's crisscrossing and comparing everything that's different between the two vectors. So they're like polar opposites in that way. And that might, if that sticks with you, help a little bit memorize this formula. Then for the y, I'm comparing z and x and subtracting the other z with the other x. And for the z, x and y subtracting the other x and the other y. Does that make sense? Kind of. You probably still don't really understand. Okay, sure, fine, but why? Don't worry too much about that. Again, you know, we're just scratching the surface with this stuff, so it makes it hard. All right, let's take a look at an example, and I'm going to give you a little trick that will help you also not only do the work, but remember how to do these things. So the trick goes something like this. A couple of different ways of doing it. This is how I do it. I'm going to start with A. So I'm doing A cross B first. Okay, so let's write that down. A cross B. We're supposed to do both A cross B and B cross A. If I'm doing A cross B, I take A and I start with it. And because the cross product starts with the Y value of A, that's what I'm going to start with. And just off to the side, I'm going to write down the Y value of A, then Z value of A, then X value of A, then Y value of A again. It'll be very obvious why we're doing this in a moment. Then below that, I'm going to start with the Y value of B, then Z value of B, then X value of B, then Y value of B again. Some people start with X and write it out kind of twice and then cross out what they don't need. I just start with what we need. But you can do it however you want. Okay. I'm going to write this out nice and long for the first time doing it. So what do? So watch carefully. Cross product says I do the Y value of A times the Z value of B. So that's those two. This is the Y value of A. This is the Z value of B. It's easy to remember because it's a cross. I'm crossing over. So it's 1 times 6. Then I subtract. And it's now the Y value of B, which is this one, times the Z value of A. So I go this times this minus this times that. And then we just continue through all the pairs. That's my X value. Okay, for the next one, I bump over one, and now I'm doing the Z value of A times the X value of B. Well, take a look. The X value of B is 4. The Z value of A is 3, so that's 3 times 4 minus 6 times 7. Do we see how this works? Still not hard. All we're doing is multiplying and subtracting. The only thing that doesn't matter, 6 times 7, 7 times 6, I don't care how you think of it. Like, that doesn't matter, obviously. But subtracting order matters. Okay, and finally, I'm going to do the last cross like that. So that's 7 times 3 minus 4 times 1. Okay, and this works out to 6 minus 9, 12 minus 42, 21 minus 4, which works out to negative 3, negative 30, and 17. Vector. The result is a vector. Questions? Yeah. I started with A on top, and I started with the Y value of A. 1, 3, 7, 1. 1, 3, 7, 1. So you start at y, and then you go to z, then you go back to x, and then y again. Like in order, you know what I mean? But yeah. Starting with y. And starting with A on top and B on bottom. Y, Z, X, Y. Okay, let's do B cross A. What is interesting or curious about this? Doing A cross B, then B cross A. Like, why would we do both? So, well, we'll do both and see what happens. Is it the same? Because like dot product we noticed was the same. A dot B is the same as B dot A. If we're just talking integers, A times B is the same as B times A. So we're going to explore and see, but you may have already thought about what's going to happen. We're going to explore and see what happens if order matters. Okay, so again, if I'm writing this out, now I start with B on top. 3, 6, 4, 3, and then A, 1, 3, 7, 1. So this is 3 times 3, which is 9, minus 1 times 6, which is 6, so 9 minus 6. 6 times 7, which is 42, minus 3 times 4, which is 12. 4 times 1, which is 4, minus 7 times 3, which is 21. And Daniel, you were exactly right. You get the same values, but the signs are switched. So you get a vector that's collinear with the first vector, but opposite. Both of those are orthogonal to both A and B. And they have the same magnitude, but they're in opposite directions. So this is important. A cross B is not equal to B cross A. Order matters. A cross B turns out is equal to the negative of B cross A. Yes, Summer.
So what happens if just X and Y products?
Good question. Cross product in two-dimensional space doesn't really make any sense. It's not a thing. That's the reason why we didn't do it until after we'd looked at vectors in 3 space. It really only makes sense to talk about it in 3 space. Okay. But the dot product exists in 2 space as well as 3 space, both. Okay, let's do some stuff with cross product. So you can go ahead and try this one. Find A cross B. This little trick, I would actually write it out every time. Some of you, if you practice enough or if you're good at mental math, I'm sure you could do the work without it. That's up to you, but my encouragement would be to write this out every time. So 1, -3, 4, 1. It only takes a moment. It also, in a lot of cases, will allow you to skip writing out the rest of it. This is really useful to make sure that you get all of the details correct. Okay, did we get 6, -18, and 2? Anybody else finished? Yeah? I suppose if you wanted to find other orthogonal vectors, you could scale this down. It turns out you could divide all 3 of those by 2. 3, -9, and 1 would be collinear, right? So it would be orthogonal to both A and B. Or I could multiply through by -1, or I could scale it up, multiply by 2, 12, -36, and 4. Like you could do all kinds of things if we said find 10 vectors that are orthogonal to both. You would take the cross product and just multiply by all kinds of numbers. We won't ask that then.
So when you're finding the cross product of like A cross product B, like will it be wrong if you write something that is collinear to the vector?
Yes. If it just says find a vector orthogonal to both, you can do whatever you want. You could guess and check if you wanted to, although that would take forever. I don't know why you would. You could take the cross product and then, I mean, it's extra work, but write another one that's collinear, sure. If it says find A cross B, no, A cross B is a particular vector. Yeah. Okay, now prove that A cross B is orthogonal to both A and B. Here's a great example of a question that might appear on a test. What is this actually asking us to do? How am I going to show? This is the kind of thing where people are like, I don't really know what this is asking. But it turns out once you know what to do, it's easy. What's it asking? Do the dot product and see if it's 0. Exactly, just like our learning goal from yesterday. Okay. To find a vector that's orthogonal, we did a trick yesterday that works, or you can take the cross product. To check if two vectors are orthogonal, you're probably going to use the dot product. Okay? So, first we're going to start with A cross B, which we've already done, and dot that with A. So that's A cross B. Dotted with A will be 6 times 4 plus -18 times 1 plus 2 times -3. Don't be surprised. 24 minus 18 minus 6, it's 0. Don't be surprised. It was supposed to work out that way. I already told you that this is what happens. If you wanted to check your work on a test, after you take the cross product, you could check and see to make sure that it's orthogonal to each quickly in your head or whatever. Double check, right? Therefore, A cross B is orthogonal or perpendicular to A. But we have to check both. So you can go ahead and do the next one. This would be very likely a question on a test would be something like find, given vectors A and B, find a vector orthogonal to both and show that it's orthogonal to B. Maybe not show it's orthogonal to both. Maybe it would be. Maybe just show that it's orthogonal to one. And what is that question really saying in a roundabout way? Take the cross product and then dot it with whatever vector. But these are the kinds of little questions, like I said, we were taking up the learning goal or talking about it before. If you don't understand that's what it's asking, then the test would be tricky. It'll be difficult. Okay, and I hope you got that done. Sure enough, dot product works as 0 there as well. Okay, questions? Some properties of the cross product. We've talked about these for the other operations. We've talked about how vectors don't follow the same sort of BEDMAS rules or the same properties as just working with real numbers. but they do hold some of the properties. So what property would this be? Distributive property, and it does hold. Oops. Turns out what's kind of interesting is if I'm crossing in the beginning or if I'm crossing in the end, that matters. We just saw A cross B is not the same as B cross A. So this distributive property would still be true, but it's sort of distributed in the other way, which is not something we see very often. If this ever came up, which generally just, in the nature of the stuff that we do, it doesn't, but it could be on a test. I could give you a question like simplify the following expressions, right? Where it would have something like this, and you would have to cross it with C in the end to preserve that order. It's kind of different. Okay, and the same obviously would hold true for subtraction if it was B minus C or A minus B. Obviously, it's still going to work. I mean, think about it. What is the result of adding two vectors? See, this should be an easy question. I'm sure it is. Most of you probably know, but a vector, right? We get a vector when we add two vectors, and a vector crossed with another vector will work fine. So this is perfectly good. This is perfectly good. And, you know, distributive property does hold. Okay, a couple more examples. One quick to just sort of show, you know, keep us on our toes, make sure that we're thinking. The test is there'll be a couple of diagrams, those vector diagrams that we did questions on from the first day. There'll be some of those. And there will be a lot of questions where it's like, given vectors A, B, C, given vectors U, V, W, do a whole bunch of different things. Determine this operation. Find a vector orthogonal to both U and W. Show that it's orthogonal to W. All kinds of different things like that. Okay, that's what the test will be. So I could take the cross product of U and W and the cross product of U and V and then subtract, but does anybody see a slightly easier way of doing this? Yeah, so I can use those properties that we were just doing backwards and like factor the U out and cross it with W minus V. On a test, whether you did it one way or the other obviously wouldn't matter, but just to show that this is a little bit less work because I'm only doing one cross product and I'm doing subtraction as well. So this is going to be U crossed with W, which is -1, minus V, which is -2, so plus 2. 2 minus -4, so 2 plus 4, and -4 minus 6. This is a vector, sorry. Which will be U, which is 1, 2, -3, crossed with this result, which is 1, 6, -10. We good? You don't really have to copy me. You can, I'm sure you can figure this out yourself. 2, -3, 1, 2, 6, -10, 1, 6. So this is -20 minus -18. -3 minus -10. 6 minus 2. Any questions? Okay, last example. I want you to try this one on your own. Again, this is the kind of thing where it's not telling you exactly what to do. It's not walking you through the steps. Part A, do this. Part B, do this. Part C, do this. It's just saying, do something, and you have to know all the parts. Not super complicated, but again, if you read this question and you know exactly what to do and you just start doing it, it's fantastic. That's where you want to be. So the very first part that you really want to be aware of, find a unit vector orthogonal to A and B. That's saying cross product. And then what do I do? If I want a unit vector that's orthogonal to both. Find the magnitude, and then just write out the vector over top of the magnitude like that. Okay, so again, to find this vector, I did 8 times 5, so 40 minus negative 3. 40 plus 3 is 43. 6 minus 30 is negative 24. 6 plus 16 is 22. Find the magnitude with this little formula, and then just write it out like that. Any questions? So the worksheet that's posted is for today and tomorrow. You're only doing questions 1, 2, 4, and 5 today, so skip 3, and there's also 6 and 7. Those will be for tomorrow.